Hello everyone, this is Greg Stitt from the University of Florida. In this video, I will be continuing with the training modules for the Intel Platform Acceleration Card using the Intel Dev Cloud. This will be the first video on how to design AFUs using register transfer level code. And in this video, I will cover the basics of AFUs and then look into how you can perform memory mapped I/O over CCI-P or the Core Cache Interface Protocol. So just to remind you of some of the terminology I introduced in the original video, Intel refers to functions that you implement inside the FPGA as acceleration functional units or AFUs. So in these slides, I'm going to demonstrate how you create AFUs using register transfer level code. I will go over the basic requirements of every AFU. And then I will talk a little bit about the different ways that AFUs can communicate with the processor. Primarily, I will focus on how you can use memory mapped I/O to communicate between the processor and the FPGA. The FPGA or the AFU is also capable of directly reading and writing to the processor's memory. So that will not be covered in these slides, but that is another form of communication that can happen across the Core Cache Interface Protocol. So I will be talking solely about RTL issues in these slides. You of course have to write software that will interface with an AFU, and you do that using the OPE software API, but that will be discussed in a separate video. I just want to remind you that the code examples that I use in these slides, in fact for the entire RTL training, are provided at the link shown at the bottom of the slide. And those examples include the software code and the OPE interface that you need to communicate with the hardware that I'll be explaining in these slides. So this slide here shows some of the design considerations for creating register transfer level AFUs. So a designer has several things that they're responsible for. First of all, they must identify the function that they want to accelerate, then need to create or identify potential parallelism in that function. So for FPGAs, typically the type of parallelism you would be looking for is deep parallelism or pipeline parallelism. Pipelines tend to work really well in FPGAs for streaming data because although the pipeline itself can take multiple cycles or even thousands of cycles to generate a single output, that pipeline can start new inputs before the previous outputs have finished. So in the ideal case, the pipeline can output an output every cycle once the pipeline is filled. And this tends to work really well with data streams where you have new inputs arriving continuously. So once you have figured out how to exploit a large amount of parallelism in the function to be accelerated, the designer would then have to create that parallel circuit in a hardware description language. So System Verilog, Verilog, VHDL, those are the three most common register transfer level design entry methods. So one of those three would almost certainly be what you would use. You would then have to test and verify the AFU functionality and make sure its performance is what you were looking for. And then you would have to integrate that AFU into software. Most likely the original software for your application. Now Intel does provide a set of tools to help you with some of these things. So Intel has this OPE API. This is a software API to enable software to communicate with the AFU in a more abstract way so that you don't have to deal with PCI Express transfers and things like that from software. Intel has this ASE or the AFU simulation environment. This is an incredibly useful environment that allows you to do hardware-software co-simulation. So once you have your register transfer level code, you need to be able to test it in simulation. Well, normally you would do that by creating a test bench, but creating a test bench in this environment would be very difficult because it has to mimic whatever the software is doing on the processor, and that would be an incredible amount of work to have to create that test bench. So what ASE does is it allows you to just execute your software code, and it communicates with the register transfer level code all within an RTL simulation. And then finally, Intel also provides Cordis. This is responsible for doing all register transfer level synthesis. It obviously does a lot of logic optimizations, things like that. It does placement and routing. and it also assists with timing closure. So when creating any AFU using registered transfer level code, unless you change some configuration settings that I'll talk about later, the top level interface for that AFU is going to be provided in this CCI-P standard AFU system verilog file. And what this does is it basically provides you with the basic interface to the AFU that consists of clocks, it has resets, it has some status signals, but most importantly for the purpose of these slides is this interface is what provides you with the CCI-P structure that enables communication with the host processor. So the slide here shows what that system verilog would look like. It's basically a set of clocks. So there's a primary clock that runs at 400 megahertz. There's primary clock div 2, which runs at half that, div 4, which runs at a quarter of that. There's U clock, which is basically a user definable clock. There's a reset. There's some other information about the power state and about detecting CCI-P protocol errors. I'm not going to talk about that in these slides in this presentation. You can find more information on that in the Intel documentation, but I am going to spend a lot of time talking about the port signals you see at the bottom of the interface, which is the CCI-P receive port and the transmit port. So before I get to talking about how exactly CCI-P works, I want to talk a little bit about some of the basic requirements of AFUs. And the first thing you should be aware of is that an AFU does not fill up the entire FPGA. It exists within what's called a partial reconfiguration or a PR region. And what a PR region does is it basically allows that region of the FPGA to be reconfigured without changing the rest of the FPGA. Now, if you look at the figure on the right-hand side of the slide, that figure shows that the FPGA is divided up into two sections. One is for the FPGA interface manager, and the other is for the AFU. So Intel has specific terminology for the bit streams that are used to program each one of these PR regions. If you're not familiar with the term bit stream, it's basically a sequence of bits that configures the FPGA to do what you have told it to do in your registered transfer level code. So Intel has the green bit stream, which is what is responsible for configuring the PR region that has the AFUs in it. And then there's the blue bit stream, which is what configures the PR region that has the FPGA interface manager. So typically, a blue bit stream will be provided to you by Intel to configure that portion of the FPGA so that you are provided with an interface to your AFU. And then to modify the AFU and the FPGA, you would load in a new, what they call green bit stream. So one other requirement for any AFU is that all of its top-level I/O has to be registered. Now this requirement comes from the fact that in an Intel FPGA, any PR region has to have registered I/O. And since the AFU exists in a PR region, it has to meet that requirement. The good news is in the provided code, you don't really have to do anything to accomplish this. There is this CCI-P interface reg module that you can find in the CCI-P standard AFU system verilog file. And if you open up the code for that module, you'll see all it does is register the I/O, and so you don't have to do anything else. So in order to simplify the explanation of how to create AFUs at the registered transfer level, we've created a simplified AFU module that gets instantiated within the top-level file I was talking before. So if you look at the right-hand side of the slide, we have this simplified AFU module that's shown at the top right, and then at the bottom right, it shows where that gets instantiated within the CCI-P standard AFU. So we did this to make several simplifications. So first of all, since for these training examples, we're not going to be using all the clocks that are provided, the simplified AFU just has a single clock. Now you can connect this to whatever clock you want that's specified in the CCI-P standard AFU instantiation of the AFU module. For these examples, it's just going to be connected to the primary clock, but you can change that if you needed to do something else. We also have a single reset. The other thing we did was we simplified the CCI-P interface names. So in CCI-P standard AFU, they had these big long names that kind of implied what their purpose was, the direction of the communication, and that it was for receive, and what clock it was based on. So to keep things simple and to have these signal names be a little easier to work with on slides, the AFU interface just calls the receive port RX and the transmit port TX. And I need to point out that you can follow along with all of the code for the example I'm going to explain in the remainder of the slides. If you go to this CCI-P MMIO example, that is on the GitHub repo for all of these training modules, and the link for that is shown at the bottom part of the slide. So another issue to be aware of when creating an AFU is that there is information about the AFU that has to be accessed by both the software code, C++ or whatever language you are using, and by the register transfer level code. So two examples of this would be the name of the AFU and then the unique identifier that identifies that AFU. And so if you were to do this in a quick and dirty way, you could basically put that information manually into a header file in the C++ code. You could put it manually to wherever it's needed in the RTL code. But that can lead to kind of nasty coherency issues because say you change the identifier, you change the name, or you change some other shared information. Well, if you change it in the header file for the C++ code, but forget to change it in the RTL code, that's going to cause problems and vice versa. So Intel's framework provides you with a kind of a more elegant, a safer way of dealing with this. So what you do is you take the shared information that is needed by both C++ and RTL code, and you specify it in a JSON file. And now all of the compilation scripts and simulation scripts and synthesis scripts will automatically generate header files for both the software code and the RTL code that have this information available. And it's usually in some form of a constant. So taking a look in a little bit more detail at this JSON configuration file. So in general, it has a bunch of configuration options. I'm not going to go over all those possibilities, but they are documented in all of the Intel documentation. So for this simple tutorial where we're just looking at how to create a basic AFU, there's only two things we really need to specify. One is the name of the AFU, which you can see at kind of the bottom of the slide here. In this case, I'm just calling it AFU. Obviously, if you were designing something specific, for some specific purpose, you would give it a more meaningful name. The other important piece of information is the universally unique identifier, the UUID. And you produce this by running UUID gen from the command line in Linux, and it will just output this identifier. You just copy and paste it into the JSON file here, and you now have a unique identifier for your specific AFU. Now that's important because if you're using this in a situation where the FPGA could potentially have different AFUs loaded at different times, you want to make sure that the right AFU is loaded before you actually execute your application. And that's what you use this identifier for, is you basically ask the FPGA to provide you with an AFU that has this particular ID. If it doesn't, it will tell you, and then you can have appropriate error handling. So there's a lot of other information in here. So the AFU top interface, kind of the class parameter there, that is what specifies the name of the top level file for the AFU. So unless you have a good reason to change it, I would just leave it as CCI-P standard AFU. All right, so let's take a look at this core cache interface protocol. Its purpose is to enable communication between software running on the host processor and the FPGA, or the AFU in the FPGA. And it provides two different communication mechanisms. The first is memory mapped I/O, which is what I'm going to be explaining in these slides. Memory mapped I/O gives the processor access to FPGA resources by just reading from or writing to registers within the FPGA's address space. All of these requests are initiated by the CPU, so the FPGA just responds to the CPU's requests. And it is capable of supporting both 32-bit transfers and 64-bit transfers. 64-bit transfers have to be implemented for reasons I'll explain shortly. 32-bit transfers are optional, but are possible. So the other form of communication over CCI-P is that the FPGA can directly access the memory of the host processor. So I do not explain that in these slides. That's considerably more complicated. But the way this works is that the FPGA, if it needs to access data that is stored in the processor's memory, it requests a specific number of cache lines from the memory, and then those arrive to the FPGA over CCI-P. One of the main reasons that accessing CPU's memory is more complicated than memory mapped I/O is those cache lines can actually arrive out of order, and so reordering them requires some additional logic that I will explain in a later video. All right, so what are the trade-offs between these two different forms of communication? Well, for memory mapped I/O, first of all, it's really easy to use. As you will see shortly, it can be explained in just a few slides. Its big disadvantage is that it provides pretty low bandwidth communication between the processor and FPGA. So you really only want to use it for kind of control signals or for just non-streaming inputs that require low bandwidth. Now, communication with the host processor memory, that provides you with a lot higher bandwidth. It's very useful for streaming in large amounts of data from memory or accessing large arrays, but it's considerably harder to implement and will be the subject of a future video. This slide here shows the basic structure of the core cache interface that is exposed to an AFU. So it looks a little overwhelming, and there are a lot of signals here you have to understand when fully utilizing CCI-P. But in this presentation, we're only looking at memory mapped I/O, which uses a small subset of this. And so if we just ignore all of these signals, the basic structure of the interface consists of one receive port and one transmit port. And these are named from the point of view of the FPGA. So the receive port is where the FPGA receives data from the processor. The transmit port is where the FPGA sends data back to the processor. And within each port, there are several channels. So you'll see there's a C0 and a C1 on the receive port, and a C0 through C2 on the transmit port. All right, so we're going to look at memory mapped I/O writes first because they are a little bit easier to understand. So writes transfer data from the processor into the FPGA. And one of the reasons they're easier to understand is writes only use channel 0 of the CCI-P receive port. So there's only a few signals we have to monitor. So the first signal that we have to take a look at is the channel 0 MMIO write valid signal. So CCI-P asserts this signal to specify that the processor is writing data into the FPGA or into the AFU. And so when that signal becomes 1, it's active high. Whatever the address and write data happen to be at that point in time, that is what the processor is trying to write into the FPGA. So one thing to be aware of is that CCI-P provides no explicit acknowledgement system for MMIO writes. So we're going to see something different for reads. But because there's no explicit acknowledgement, what that means is when CCI-P provides write data to the AFU has to write that data somewhere in that cycle, otherwise it's going to disappear. So new write data could potentially show up every cycle. In practice, it won't because the communication across PCI Express isn't fast enough for that to happen. But if you change that interface, it could happen. So the protocol at least requires you to be able to respond every cycle to writes. So one thing to be aware of is that I have made some simplifications in this timing diagram. So the core cache interface does not actually have a signal in channel 0 that is called HDR.address. So it does have a HDR signal. This is just a header, but it is used for various purposes. And I will explain this once I actually start showing code, why I've made this simplification to use a different name. Another thing to be aware of, it's not explicitly shown in the timing diagram, but all of the provided addresses are for 32-bit words. So if you are doing a 64-bit transfer, you have to make sure that you are only using even addresses, otherwise it will cause problems. Here we have some sample system Verilog code that shows how to implement a memory mapped I/O write to a 64-bit register that we've mapped to address 0020. Now there are a few simplifications we made in this code compared to the code that's provided in the repository, and that was just so that we could fit it on a single slide, but the basic idea is shown here in the slide. So if you look at the top of this code, we have a 64-bit user register. That is going to be the memory mapped register. Just beneath that, we see two lines of code where it says, get the header for an MMIO request. So this is what I was referring to on the previous slide, where I said there isn't actually a C0.header.address signal. So there is a C0.header signal that's part of the receive port, but it's used for different purposes depending on the context. So what we have to do is essentially cast that header into this custom type that is shown here in order to get an MMIO header. And then if we work our way down, we have this always flip-flop block. So basically on every rising clock edge, we are checking to see if on the receive port or on channel 0 of the receive port, if the MMIO write valid signal is asserted. If it is asserted, that means the processor is currently trying to send us data, and that's the CCI-P is telling us that inside the AFU. So now we just need to decode the address that is being provided in that same cycle. And in this simple example, we only have one memory mapped register, so there's only one possibility. So if that address is 0020, then we know the processor is trying to write to our custom register here. And so we just take the data that is on channel C0 of the receive port, store it into our user register, and we have successfully implemented a memory mapped write. So one thing that I always suggest doing anytime you're writing register transfer level code is to make sure you understand what circuit gets synthesized from that code. That keeps you from writing code that gets synthesized into something that is either won't work or is just incredibly inefficient. So let's take a quick look at what would most likely be synthesized from the code we just saw on the previous slide. So the non-blocking assignment that happened on the rising clock edge for the user register, that assignment will synthesize into a register, which is exactly what we wanted. We then had that case statement that compared the address with the address that we assigned to our register. So that's just going to become a comparator. And then the register is going to be updated anytime two conditions were true. First, when the address matches 0020, so when the address coming in from the processor matches the address of the register that we were trying to write to, and when the MMIO write valid signal is asserted. So basically you have an AND gate, you have a comparator, they form logic that creates the enable for a user register, and that user register just stores the incoming data on channel C0 of the receive port anytime those conditions are true. So it's not necessarily guaranteed that it will synthesize to exactly this, because different FPGAs have different types of lookup tables, and they might do different types of logic optimization to better use those lookup tables, but it will likely be something very similar to this. All right, so let's take a look at reads now. Reads are a little bit more complicated than writes because the core cache interface gives the AFU multiple cycles to respond to a read. So the protocol has to be a little bit more complex. The way that CCI-P signals that a read is occurring is similar to the way a write works. So on channel 0 of the receive port, there is an MMIO read valid signal. And when CCI-P asserts that, it basically tells the AFU that the processor is trying to read something from the FPGA. And the address of that read is provided as part of the channel 0 header on the receive port. And just like for writes, the address isn't an actual part of that header, but you have to cast it to another type, and then you can get the address from that same shared set of wires. Same thing for the transaction ID. So basically, when an MMIO read occurs, CCI-P tells the AFU by asserting the MMIO read valid signal while providing an address and a transaction ID within the same cycle. Now the AFU takes that address, it grabs the data from whatever resource happens to be mapped to that address, most likely a register, so it would read from the corresponding register. And then some number of cycles later, when that data is available, it provides the data on channel C2 of the transmit port, so that there's a data signal there. It puts the read data on C2.data of the transmit port. It provides the transaction ID for the corresponding transaction, and in the same cycle, the AFU would assert the MMIO read valid signal of channel 2 of the transmit port. So that basically tells CCI-P that the data that was requested for the read is now available, send it back to the processor. So the reason why the protocol provides this flexibility in timing, where it basically gives you multiple cycles to respond to a read request, is because there could be situations where you want to memory map things other than registers. So if you've memory mapped a memory or just some other resource that requires more than one cycle to access, well, then you can't respond to a read request within a single cycle. So this flexibility gives you the capability of creating more flexible memory maps than you could if it had that one cycle restriction. However, one important thing to note is that most use cases for AFUs are probably going to be mapping these addresses onto registers, in which case the AFU can respond within a single cycle. And so if you can do that, it makes the implementation of memory mapped reads a little bit simpler. So on this slide, I've illustrated a simplified timing diagram where the read response always occurs one cycle after the request for the read. So in this case, basically, as you can see in the timing diagram, so address 0 shows up for transaction 0. In the next cycle, you see on the transmit port, the AFU is responding to that by providing the data, read data 0 for address 0. And you see it's also responding to transaction ID 0. In that same cycle, there's a new read request coming in for address 1, for transaction 1. In the next cycle, the AFU provides the data for that, and so on. So my suggestion would be, if you can make your AFU implement this type of read response, it will make the RTL code a little bit simpler. If you need to, you can take multiple cycles, and in fact, you can respond to read requests out of order by just providing the corresponding transaction ID whenever that data is available. But it is definitely easiest to use the method that is shown on this slide, because you don't really have to save the transaction ID then. It's always going to be the transaction ID from the previous cycle when you respond. This slide shows how you would go about creating system Verilog code to implement one of these memory mapped reads using the simplified timing model where we respond within a single cycle. This is basically going to complement the write example you saw earlier, where we wrote to a 64-bit register that was mapped to address 0020. Here we're going to write the code that handles reads from that same register. So we have the always flip-flop block, basically on every rising clock edge. So there's reset code here that is not included on the slide just to keep it simple, but you can see the code example for exactly what gets reset. So on every rising clock edge, we're basically going to clear the MMIO read valid signal on channel 2 of the transmit port. So basically by default, we're going to respond saying that we're not responding to a read in this cycle. And of course, we can override that later if we need to, but in most cases, in most cycles, we're not going to be responding to a read. Next, we're going to check to see if a read request is currently occurring. We know it's occurring if on channel 0 of the receive port, the MMIO read valid signal is 1. So CCI-P tells the AFU a read request is occurring when that signal is 1. So after that if, we know a read request is occurring, so we just need to check we need to grab the transaction ID And if we're assuming we're going to respond within a single cycle, this makes it really easy. So we don't need to actually save that ID. We can just use a non-blocking assignment to the transaction ID on the header of channel 2 of the transmit port. We can assign it the current transaction ID because that non-blocking assignment will create a register. So it essentially creates a 1 cycle delay of the incoming transaction ID. So we delay that incoming ID by 1 cycle, and that's exactly what we want if we want to respond within 1 cycle. Similarly, we assign the MMIO read valid signal on the transmit port. We give it the value 1, so that 1 cycle later it is also asserted. And then finally, we just have to provide the corresponding data. So we have a case statement that looks at the address that is requested for the read. We go through the possible values that have been mapped to the FPGA's memory address space. And when it's 0020, we basically assign the data port of channel 2 on the transmit port to the value that is stored in the user register. And all of those assignments take one cycle. They're basically get implemented as registers, so it's a 1 cycle delay. So if your AFU is capable of handling reads within a cycle, this is basically all you have to do, and you can extend it to as many registers as you want just by adding more addresses to the case statement. So again, we should always try to understand what gets synthesized for a given piece of code. So that is what this slide looks at here. So for every non-blocking assignment we have on a rising clock edge, the synthesis tool is going to create a register. We already had one of those registers when we implemented the MMIO write. That was what created this user register. But we have 3 more of these non-blocking assignments now. So we have one for the transaction ID on the transmit port. We have one for the data on the transmit port. And we have one for the MMIO read valid on the transmit port. So those are basically the 3 signals that we need to tell CCI-P that we have responded to the read. And we use registers to do it because we're using that simplified model where we always respond within 1 cycle. Now, if we look at the rest of the code, we need to figure out how this all works. So there could potentially be a bunch of memory mapped registers. And so I've kind of assumed that is the case in this figure here on the slide. So you'll notice in front of the data register on the transmit port, there is a MUX. That would be used to select between the different memory mapped registers. So I'm only actually showing the user register that we have, but you would probably have more than that. And then that MUX is going to select from all of those possible registers or other types of resources that you can read from. And it's going to do that based on the requested address. So there's going to be a comparator for every one of those possible resources that you could read from within the memory map. So in this case, we just have the 1. So we have the comparator that compares the address to 0020. Then the output of those comparators have to go into something like an encoder, which would create a select for the MUX, so that based off the address, the MUX is essentially passing through whatever the requested data was. If we look at the transaction ID register, its input is simply just the transaction ID for the incoming request, because we just want to delay it by 1 cycle. And then we see something similar for the MMIO read valid. So on the transmit port, it's just a register whose input comes from the read valid signal on the receive port, because again, we're just delaying it by 1 cycle. We can also use that same signal to enable the transmit data signal, because anytime there's an incoming request, we want to update the data in that transmit port, the data register transmit port. And so the timing of that signal is exactly what we want for that to happen. So again, it may not synthesize to this exact circuit, but it's going to be something very similar to this. So one thing you need to be very careful with is every AFU has to be able to respond to MMIO reads for specific addresses. And those addresses basically provide information about the specific AFU. So you see on the slide on the left, basically at address 0, there's information that just specifies characteristics of the AFU. So you can most likely just copy and paste that across all the AFUs that you implement. At address 2 and 4, there is something that is very important that is also specific to each AFU that you create. And so that is where you need to specify the universally unique identifier for the AFU. So when we talked about that JSON file and you created the identifier there using the command line tool, when you compile a code or when you simulate the code, that identifier gets included in a system Verilog header, and you can refer to that in the examples using this AFU ID logic that you see on the right-hand side of the slide. So basically, if there is an MMIO read request to address 2, that is the processor requesting the lower half of the ID, the AFU's ID. If there's a read request from 4, that is the processor requesting the upper half of it. So the first thing that any piece of software will do that interfaces with an AFU is make sure that the correct AFU is loaded into the FPGA, and this is exactly how it does it. It does an MMIO read to get the identifier of the AFU. If it's not the correct identifier, then it's obviously not going to work. And then at address 6 and 8, there's just some reserved space. You shouldn't do anything with that. So in all of your AFUs you create, I would just copy and paste this, and then if you have the AFU ID specified in the JSON file like I showed earlier, then it should automatically update for every AFU. All right, so just to quickly summarize all of the steps we had to follow to create an AFU using register transfer level code that implements memory mapped I/O. First, we had to specify all of the relevant information about the AFU in the JSON configuration file. At the very least, this was the identifier for the AFU. We then had to assign addresses to every user register or whatever resource we wanted to implement as part of the memory map within the FPGA address space. So what we saw is 64-bit transfers have to be supported because there is information about the AFU that has to be returned for any AFU. You can optionally implement 32-bit transfers if you have a reason to. But if you do use 64-bit transfers, you have to use even addresses because the addresses are for 32-bit words. So every AFU has to implement MMIO reads, even if you don't have any resources you want to read from, because that is the way that software requests information about the AFU. And those reads can be implemented across multiple cycles, or you can even respond to them out of order. But as I showed, the read logic is simplified when you can respond within a single cycle, because in that situation, you're basically just delaying the MMIO read valid signal and the transaction ID by a cycle by using a register. MMIO writes are a little bit easier. MMIO writes have to be handled in the cycle that they show up on CCI-P, otherwise the data will be lost. And just a quick reminder, all of the code that I used for this example can be found in the repository shown at the bottom of the slide. It also includes how software communicates with this and probably has a lot more comments than I was able to include in these slides, so I'd recommend that everybody check that out.